Here are explanations for the multiple choice questions on the practice test. So we're told that the probability that a randomly selected student eats breakfast is 0.57. Probability that this randomly selected student flosses their teeth is that a randomly selected student flosses their teeth is 0.8. And the probability that the randomly selected student does both is 0.46. Now, these probabilities are not disjoint since they have an overlap, and we can use a Venn diagram for non-disjoint probabilities in order to break down the probabilities. If it can be a useful thing anyway. So, first thing is draw the two circles and put the 0.46 in the middle. Now, here's the probability of breakfast over here, this circle right here, and this circle is the probability of flossing teeth. Now, the probability of breakfast is 0.57. Part of that is the overlap, which is 0.46. You can see that's included in the circle. So 0.11 is the part that's not in the overlap. And so this is the probability that they eat breakfast but don't floss their teeth. Here's the probability they do both. Here's the probability they don't eat breakfast but do floss their teeth, and that's 0.34. Now, so anyway, that's the answer to the question, namely 0.11. The probability that they eat breakfast, 0.57, but does not floss, that equals the probability of eating breakfast minus the probability of eating breakfast and flossing. So 0.57 minus 0.47, which is 0.11. Okay, the probability they eat breakfast or floss, which is symbolized by this symbol right here, which is probability of B union F, and this is U is the union symbol, which stands for or, equals the probability that they eat breakfast plus the probability that they floss minus the probability of eating breakfast and flossing, which is 0.57 plus 0.8 minus 0.46, which is 0.91. Okay. 9 students, 5 juniors and 4 seniors are randomly picked. These probabilities are disjoint. The probability of being a junior, probability of being a senior have no overlap. Being a junior means you can't be a senior at the same time, and vice versa. When the probabilities are disjoint, use a tree diagram to determine the probabilities. So here's the first choice. The probability you get a junior is 5 out of 9. The probability you get a senior is 4 out of 9. Second choice, here's the second choice, is the second set of branches, is, okay, given that you got a junior, the probability you get another junior is 4 out of 8. There's only 8 students left, and there's only 4 juniors left. Given that you got a junior, the probability of getting a senior, see, we're on the junior branch here, so we're going to say given you got a junior, we're going to probably get a senior, is 4 out of 8. They're the same, and they add up to 1. Now, here's the branch where you got a senior the first time. Well, given you got a senior the first time, the probability you get a junior on the second pick is going to be 5 out of 8. And given that you got a senior on the first pick, the probability you get a senior on the second pick is 3 out of 8. And again, these two add up to 1, these add up to 1. So the question is, what's the probability to get 2 juniors or 2 seniors? Well, the probability of 2 juniors, junior and a junior, is the probability of a junior times the probability of a junior given that you got a junior. So this is junior second, this is junior 1 times junior second given you got junior 1. So that's going to be 5 out of 9 times 4 out of 8, which is 5 out of 18. Now the probability you got 2 seniors, senior and senior, is going to be the probability of getting a senior the first time, 4 out of 9, times the probability you got a senior the second time, given you got a senior the first time, 4 out of 9 times 3 out of 8, or 3 out of 18, for a total of 8 out of 18. So you're going to add them together. You're going to take the probability of junior and junior plus, or okay, it's plus. So this is the probability of junior and junior, or the probability of senior and senior. So you're going to take the two probabilities and add them together. And you can do this because they're disjoint. Okay. So we got 5/8 plus 3/8 is 5/18 plus 3/18 is 8/18, which is 4/9, and that's 0.49. Okay. 4b. 4 is B. Assuming the coin is fair, the probability of a head on any flip, no matter what's happened previously, is always 50%. However, if the question was 100 times in a row, then the assumption that it's fair, or 20 or 25, I mean 10 is pushing it. I mean the probability you're going to get 10 in a row from a fair coin is 1 out of 10, 24, which is not impossible, but you know, it's so it means if you flip the coin, you know, if you flip it a couple of thousand times, you're probably going to get a run of 10 in a row out of there. Maybe even a couple hundred times you'll get 10 in a row. This is a good thing to experiment with a simulator. But anyway, assuming the coin is fair, and it says fair coin, 10 in a row, the probability it gets ahead on any flip is always going to be 50%, including the next one after the 10th. Just, you know, if it was 100 in a row, you would have to assume it wasn't fair. 5e. The probability that somebody has a computer in their home is 0.565. And we're talking about 3 homes. What's the probability that of 3 randomly selected U.S. households, at least one owned a computer in 2001? Now, there's a couple different ways to look at this. It's definitely, first of all, it's a very simple question. Namely, if the probability, we want to know the probability of at least 1 out of 3. Well, that means subtract from 1 the probability of none. Okay, so the probability that the computers is greater than or equal to 1, the number of computers out of 3 is greater than or equal to 1, is going to equal 1 minus the probability that none of them are. Now the complement, in other words, probability that there's not a computer in the home, is 1 minus 0.565, which is 0.435. So, out of 3 computers, the probability that none of them, out of 3 households, the probability that none of them have a computer is 1 minus 0.435 cubed. So that's 0.918. So 0.918 is the probability that at least one household has a computer. Now, you could do this also with the calculator. You could do this differently with GeoMet PDF. Okay, let's see. Let's try this. So we'll do second vars and arrow up to, I'm sorry, I already went too far. GeoMet CDF, because we want 1 out of 3. 1 or 2 or 3. And so the probability is 0.565, comma 3. Okay, and we get the exact same answer, 0.917, or about 0.918, or 91.8. So you can do this 2 different ways. You can either do the complement, find the complement, which is 1 minus 0.565, and then subtract from 1 the probability that all 3 households do not have the computer, which will leave the probability that at least 1 or 2 or 3 households have the computer. Or you can do GeoMet CDF, which will give you the cumulative probability that at least 1 household is found to have a computer out of 3, putting the probability of a household having a computer first, and then the number of households you want to consider. Remember, it's CDF if you're doing at least. If you're doing exactly, what's the probability I have exactly 1 out of 3, that would GeoMet PDF. Okay, 6 is A. The probability the household has an internet boy, this has changed a lot, is 0.505. We're talking about 4 households. So what's the probability that 4 out of 4 have the internet? Well, this is pretty simple. It's simply 0.505 to the 4th. That's probability that all 4 of them have it. This is a binomial probability, but you don't need to use that. Just it's the first household has it. That's 0.505. The second, third, and fourth. It's just 0.505 times itself 4 times, or 0.505 to the 4th. Okay, number 7. A. Okay, 7. We're talking about which of the number of people we survey until we find someone who's taken statistics. Okay, this is binomial because there's no set n. Theoretically, it could be a billion people. But for the binomial probability has n, p, and x. Now, sometimes we don't know what x is, or we're trying to find the average x or something like that. But n is always set. Okay, this random variable counts the number of people surveyed until the first stat student. So it does not have a specific n, but it is binomial. I'm sorry, it is geometric. It's Bernoulli, and it's geometric. It's not binomial. B, I don't know which one. I don't know if it's even a Bernoulli event. Probably it is, but it's not one that we consider. How many people you got to talk to until you find the first 2? Again, n is not set, so it's not binomial. C, n is set. The random variable counts the number of stat students in a group of 25. This is binomial. D, the number of aces in a 5-card poker hand. The probability of each ace is not constant. Okay, the cards are dealt out and they're not replaced. So we do not have a constant probability for each ace. Probability you got 1 ace is different than the probability of 2 aces on the second ace. And the probability if you have 2, the probability of getting the third ace is definitely affected by the probability by the fact you already have 2. So the probability changes and the events, and they're not independent of each other. So it's not binomial. And E is not binomial. No set n. Okay, just we have the variable we're talking about is the number of drinks that kids drink each day. Okay, all right. Now we have the same set of answers for 8, but this time we want to find which one is geometric. Well, as we said above, A is geometric. Okay, 9, probability of a defective battery. Well, 0.995 of them are good. Let's consider this to be disjoint. You're either defective or you're not. So 1 minus 0.995 is the way you find the probability of a defective battery, which is 0.005. Now, we're asking ourselves, how many batteries we got to look at? So n is not known, but this is Bernoulli. Why? It's either defective or it's not. We'll consider the batteries to be independent. And n is definitely, well, let's see, the probability is going to stay the same for battery to battery, and we'll consider them to be independent of each other. Now, it's geometric since the random variable is the average number of batteries expected before the first defect. That's the definition of geometric. Okay. Now, the geometric probability mean, or the expected number of batteries you got to look at, is 1 over the probability of a defective battery. In other words, it's 1 over the probability of whatever event it is you're waiting to happen for the first time. Now, if it was how many batteries you got to examine before you see one that isn't defective, it would be 1 over 0.995. And that number would be very close to 1. You'd expect the first battery you look at to not be defective. But instead, we're going to take 1 and divide it by the probability of a defective battery, which is 0.005, which is 200. So you'd expect to look at 200 batteries on average, before you got to your first defective. Okay, we got the people splitting the marathon, 2 people running a half marathon, and the mean of Alice's time is 92 minutes with a standard deviation of 4, and Sharon's mean is 96, standard deviation of 2. Now we consider them to be independent of each other, which means the expected average time for Alice and Sharon is the sum of their means, 92 plus 96, 188 minutes. But the question asks, what's the standard deviation of Alice and Sharon? Well, if they're independent, then we can take the square root of the variances, which is the square root of the sum of the variances. So it'll be the square root of 4 squared plus 2 squared, since the variance equals the standard deviation squared. That'll be the square root of 20, which is 4.472 minutes, or it's rounded in the answer, it's rounded to 4.5 minutes, is the standard deviation.